Our topic that we chose to do is gravity. There are two main equations used in this topic. The first equation is F equals G times mass 1 times mass 2, all divided by radius squared, where G is a constant, which is 6.67 times 10 to the negative 11th. And this formula is used to show the pull between two objects. The next equation is U sub G equals negative G times mass 1 times mass 2, all divided by radius, where G is the same constant, 6.67 times 10 to the negative 11th, and this formula represents the potential energy. There are four other helpful equations that are used with this topic, and they are derived from these two equations.
The first equation is derived from the formula F equals G times M1 times M2 divided by R squared, and it's the gravitational pull. Okay, so since we know that force equals mass times acceleration, we know that force is equal to the mass of the object times the gravitational acceleration, and we know that force also equals G M1 M2 over R squared. So we can set these two equal to each other, and we get M2G equals G M1 M2 over R squared. Then we can cancel out the M2 and get G, the gravitational pull, equal to G, the constant, times M1 over R squared. The units of this are meters per second squared because it's an acceleration.
The second equation is derived from the equation F equals G times M1 times M2 over R squared. Since we know that F equals MA and that F equals G times M1 times M2 divided by R squared, we can set these two equal to each other. So we get MA equals G times M1 times M2 divided by R squared. And we can write acceleration in another form, so we can write it as M times V squared over R equals G times M1 times M2 divided by R squared. By doing this, we can cross off an M on each side and one of the R's on each side. So then we're left with V squared equals G times M1 all divided by R. And we could get velocity equals the square root of G times M1 divided by R, and the units of this are meters per second. This equation is the orbital velocity of a planet.
The third equation is also derived from the force equals G times M1 times M2 over R squared. And we still know that force equals mass times acceleration. So we can set that equal to G M1 M2 over R squared. And we're going to rewrite acceleration using our centripetal motion formulas and write it as 4 pi squared R over T squared equals G M1 M2 over R squared. Then we're going to cancel out the M's. Now we're going to multiply by R squared to get rid of the denominator on the right, and you get 4 pi squared R cubed over T squared equals G times M2. And then we multiply by T squared. So you get G times M2 T squared equals 4 pi squared R cubed. Then you're going to divide by G times M2 to get T squared equals 4 pi squared R cubed over G M2. And this is in seconds because it's the period. This is the period of one object orbiting another. This equation also shows Kepler's law, which says that T squared equals K times R cubed.
The fourth equation is derived from UG equals negative G times M1 times M2, all divided by R. Since we know that kinetic energy plus potential energy equals 0, we can plug in the equations for each. So 1/2 mv squared, and then plug in the potential energy equation. So negative G times M1 times M2, all divided by R, equals 0. Then we can add the potential energy to the other side. So we get 1/2 mv squared equals gm1 times m2 divided by r, and this helps us get rid of the negative. So next we are going to cross off an m on each side, and then we are left with v squared equals 2gm over r, and then to take the square root of both sides, you get velocity equals the square root of 2 times g times m, all divided by r, and this is in meters per second, and this represents the escape velocity of an object. Our first problem is number 5 from the multiple choice section, and it is: the Earth is 93 million miles from the Sun, and its period of revolution is 1 year equals 3.15 times 10 to the 7th seconds. What is the acceleration of the Earth in its orbit about the Sun? In this problem, we're trying to find g, and they give us the radius from the Earth to the Sun, which is 93 million miles, and the period, which is 3.15 times 10 to the 7th seconds. In order to do this problem, we need the two equations that we solved for at the beginning, the period and the gravitational equations, so that they are t squared equals 4 pi squared r cubed divided by g times the mass of the Sun, and g equals g times the mass of the Sun over r squared. First, we're going to use the period equation to solve for mass of the Sun. So we get mass of the Sun equals 4 pi squared r cubed divided by g times period squared. Now we can plug in our numbers that we have. So the mass of the Sun equals 4 pi squared times the radius, which is 93 million miles cubed, divided by g, which is the constant 6.67 times 10 to the negative 11th, times the period, which is 3.15 times 10 to the 7th squared, and we get mass of the Sun to be 4.798 times 10 to the 20th kilograms. Now that we have the mass of the Sun, we can plug that into the gravitation acceleration equation, and we get, which is g times mass of the sun divided by r squared. So we can plug in our numbers that we have, where g is the constant 6.67 times 10 to the negative 11th times the mass of the sun, which we found to be 4.798 times 10 to the 20th, all divided by the radius, which is 93 million squared, and we get the acceleration of the Earth to be 3.7 times 10 to the negative 6th miles per second squared.
The next problem is number 13 of the multiple choice, and it says, for any object orbiting the sun, Kepler's law may be written, t squared equals k times r cubed. If t is measured in years and r in units of the Earth's distance from the sun, then k equals 1. What, therefore, is the time in years for Mars to orbit the sun if its mean radius from the sun is 1.5 times the Earth's distance from the sun? So we are going to solve for the period of Mars using Kepler's law, which is that t squared equals k r cubed. And they give us that k equals 1. So we know the period of Earth squared is equal to 1 times the radius from the Earth to the sun cubed. If Mars's radius is 1.5 times Earth's radius, we know that the period of Mars squared equals 1 times 1.5 of r cubed. This means that the period of Mars squared is equal to 3.375 times radius cubed. Using the period equation of the Earth, we know that the period of Mars squared is equal to 3.375 times the period of Earth squared, since the period of Earth is equal to r cubed. Since we know the period of Earth is equal to 1 year, we can plug that in and get 3.375 times 1 year is equal to Mars's period squared. Therefore, the period of Mars, if you take the square root of both sides, is equal to 1.837 years on Earth. Is letter A.
This next question is number 11 from the free response, and it says, the planet Mars has a satellite, Phobos, which travels in an orbit of radius 9.4 times 10 to the 6th meters with a period of 7 hours and 39 minutes. Calculate the mass of Mars from this information. We're going to solve for the mass of Mars, and in order to do this, we can use the equation period equals 4 pi squared r cubed, all divided by g times the mass, and this will be the mass of Mars. So when we rewrite this equation, we get that the mass of Mars equals 4 pi squared r cubed divided by g times period squared. In order to start this problem, we need to take the period of 7 hours and 39 minutes and change it into seconds. And so then the period is 27,540 seconds. Now we can plug in all of our values and to solve for the mass of Mars. So 4 times pi squared times the radius, which is 9.4 times 10 to the 6th cubed, divided by g, which is the constant 6.67 times 10 to the negative 11th, times the period, which we found to be 27,540 seconds, and we're going to square that. And we find that the mass of Mars is equal to 6.48 times 10 to the 23rd kilograms.
This is the completion of Annalise and Sammy's gravity video.